Hello, good morning. Um, it's evening for me. Welcome to my basement. I got my Odie dogs down here. It's Otis. How you doing, Otis? Oh, it's my baby. You sleeping? You hanging out with Mama? Okay. Anyway, so I am not here today. Obviously, my daughter got sick earlier, and I have to take her to a doctor's appointment this morning. I will be back till later this afternoon, though, like after lunch. So if you have questions, come find me. Um, it is like 10:15 p.m. Way past my bedtime, so I'm gonna try to make this quick. I just want to make sure that we go over everything. So let's go over this Half-Life stuff first. Just kidding. So this is what we're gonna do today. So we're gonna go over the Half-Life practice. We are gonna skip the GimKit. We'll do it another day. I do want to just at least lead you to the videos about Chernobyl and Radium Girls. It's going to be under this resources and extension tab up here. I will go through the lesson on electromagnetic spectrum, drawing Bohr models and Lewis dot diagrams, and then you guys have two assignments today, two different assignments. So please don't forget about one or the other. One's really actually pretty easy. So anywho, let's go over this. Let's see if this actually switched tabs with me. Oh my goodness. How do I switch this? Lord, guys. I don't even know. Okay, so apparently I'm gonna have to record each tab individually because technology is not on my side tonight, and I just don't have the energy to fix it. So I'm just gonna splice all these together and it'll be fine. So we're gonna go over this key real quick. Let me move this out of the way. So this is the Half-Life practice from last class. So you guys remember you did the circle and you cut it and you cut it again and you cut it again, talking about how much radioactive material would decay and stabilize versus how much would still be left over. So you did have some practice problems to go with that, and that was this. So what is meant by half-life, that was kind of in the notes that we went over. It's just how much time it takes for half of the radioactive material to stabilize. So you have decayed. Decaying is the same as saying that it has stabilized. So number two is three parts. Okay, so it says if you have 100 grams of a radioactive isotope with a half-life of 10 years, how much of the isotope will you have left after 10 years? Well, it's pretty straightforward on that, right? So if you have one half-life is equal to 10 years, you have only degraded 50%. Okay, so you'd have 100 grams because that's what you're starting with. It tells you right here. You're gonna have 100 grams times one half is gonna give you 50 grams. So how much of the isotope we have left after 20 years? Same idea. Okay, so if you know that there's 20 years, you're going to divide that by how long one half-life is. So if you have 20 years divided by 10 years, that means two half-lives have passed. You're going to take your starting amount of 100, multiply it by half times one half, and it gives you 25 grams. C is just saying how many half-lives will occur in 40 years. So again, 40 years divided by how long the half-life is tells you 4 half-lives. On number three, this is when they started to get a little bit more complicated. So the half-life of plutonium-239 is 24,300 years. If a nuclear bomb released 8 kilograms of this isotope, how many years would pass before the amount is reduced to 1 kilogram? So you first need to figure out how many half-lives have actually passed. So if you have only 1 kilogram left and you started with 8, you can divide that. So we have 1 divided by 8 tells you that you only have 12.5% remaining. So you can go back in, and that's what this little picture is that I put up here. Just like with those circles you guys cut out last class, one half-life would remove 50%, another half-life would remove an additional 25%, and a third half-life would remove an additional 12.5%, which would leave you with this 12.5% pie piece. So if you have if you're looking at this, is just going to be 1 half-life, 2 half-lives, 3 half-lives. Then you have 12.5% remaining. So you know that that's going to be 3 half-lives to get to this point of 1 kilogram. Now you have to go back in and figure out how many years would have passed before, before that happens. So if you have 3 half-lives times the amount of time that your half-life is, which in this case is 24,300 years, you're going to end up with 72,900 years is how long it's going to take before that plutonium degrades all the way down to 1 kilogram. Number 4, kind of the same idea. Okay, so you have the half-life of radon 222, it's 3.8 days. How much of a 100-gram sample is left after 15.2 days? So you have to figure out how many half-lives have actually passed in that time frame. So you know that 15.2 days has passed. 1 half-life is 3.8 days. So you're going to take 15.2 divided by 3.8. That's going to tell you that you have had 4 half-lives pass. Now you can go in and multiply the starting amount, which in this case is 100 grams, by half, by how many half-lives you have. So here we're just saying 100 times 0.5, 0.5, 0.5, 0.5. So you have 4 half-lives, which is going to tell you that your remaining amount of radioactive material will be 6.25 grams. So keep in mind that the sample is not going away. Okay, so if you start with 100 grams, you still have 100 grams when you're done. The only difference is that now, in this case, only 6.25 grams is radioactive after 15 days, where in the beginning, all of it was radioactive. 5 is done the same way. So you divide, figure out your half-lives, multiply your starting amount. So you should have ended up with 8.75 milligrams on that one. It's not grams. 6, let's see. This one, it was a little tricky because you were kind of working backwards on it. So for this one, it gives you the half-life is 5.26 years. You're saying if 50 grams are left after a period of time has passed, so after 3 half-lives have passed, I now have 50 grams of radioactive material. How many grams were radioactive in my original sample? So the only difference here is that instead of multiplying by each half-life to go from your original to the final, since you're going from the final back to the original, you're going to be dividing by each half-life. So we figured out there's 3 half-lives, so we're going to have 50 divided by 0.5, divided by 0.5, divided by 0.5. This gives you 400 grams. 7 is done the same way. Okay, so you figure out how many half-lives have passed, then you're going to divide that by each half-life. Number 8 is the last one here. So this one says we have 100 grams of gold 198 decays to 6.25 grams in 10.8 days. What is the half-life? So if we have 6.25 grams out of 100 grams to start, would have been 6.25%. Okay, so you can figure out your percentage, figure out how many half-lives that is. So I went back to the pie pieces here. So we know that if 1 half-life passes, you have 50% remaining. 2 half-lives pass, you have 25% remaining. 3 half-lives pass, you have 12.5% remaining. And then 4 half-lives have passed to give you 6.25%. So at 6.25% remaining, you have 4 half-lives that have passed. Okay, so if you have 10.8 days and 4 half-lives have passed in 10.8 days, you'll just take 10.8 divided by 4. So it tells you that each half-life for this substance is going to be 2.7 days. Okay, so we are on to the notes now. So I do want to just point out that, did I get this actually work here for me? That on Canvas, under the tab where it says, okay, sorry, I'm just trying to like get rearranged and just about fell out of my chair. Anyway, so on Canvas, on the resources and extensions tab, there's like a lot of information in there. Okay, so there's a couple of videos. One is the like how Chernobyl happened. It's a 3D like replication of the scene and explains how the nuclear reactors work, how they're regulated and then like what specifically went wrong with Chernobyl. And it's pretty interesting. That one I think is like 12 minutes long, but I thought it was worth it. So if you have 12 minutes to spare, that would be a really cool video to watch. There's also a video on there about the Radium Girls, which is shorter, but that kind of gets you into also the problem of like socioeconomics. So in that time, when women were having to go into the workforce to pick up some of these jobs that were left empty when men went off to war, um, obviously only people from lower income families needed that additional income, right? So these Radium Girls were being offered quite a bit of money for the job they were doing, and they kind of made it out to be like a glamorous job. So they had these tiny paintbrushes, and what the Radium Girls did is they had this radioactive material, and the idea was is that women are like petite, and they would take this little paintbrush and put it between their lips to like make the paintbrush really thin, so they could like paint very precisely. So they were painting like the numbers on like watch faces and like alarm clocks, things like that, so you could see them in the dark. Well, these women ended up starting to like glow. So like their mouths would glow, their hands would glow. Some of them like large portions of their body began to glow, and it was like glamorized, and everybody was like, "Oh, it's so beautiful! Like, yeah, keep doing it." But the people that were having these women work knew that the radiation was dangerous. They knew kind of pretty soon, and they kept on hiring people to do it because they just wanted to make money. So um, all of these women ended up dying like horrible deaths because radiation poisoning is awful. Um, but anyway, so I digress. You guys can watch that video if you want. I would recommend it. That one's shorter. I kind of like the Chernobyl one better. I don't know. So it's up to you. But anyway, I'm gonna try to get through this pretty quickly. I know I'm gonna try to make my face a little smaller here. I have no idea how to do that. Holy my horses. There we go. Ah, there we go. I'm a little bit. All right, can I get smaller? No, can't get any smaller than that. What the heck does that do? Aha! Ooh, it's like when you change your face, like, oh, that's not good. Guys, way past my bedtime. All right, anyway, I will shut up and just get on with this. So, your objective for today, you're going to describe the principles of the electromagnetic radiation, the electromagnetic spectrum, and we're going to talk about Bohr models and Lewis dot diagrams. So, I know some of this you guys have hit on in physical science, so we'll just get into it. So, this will all lead up to eventually bonding. That's kind of where we're headed with this. So we did talk a little bit about, can I just make my face go away? I don't know how to do that. Can I make myself smaller? Oh no. No, okay. Well, we're just gonna, I'll go over here. I don't know. I don't know where to put myself. Okay. Anyway, so properties of light. We're talking about the electromagnetic spectrum. So the electromagnetic spectrum is covering a wide range of energy. What you guys are probably most familiar with of that is the visible light spectrum. So we have Roy G. Biv, so red, orange, yellow, green, blue, indigo, violet, and you have energy on either side of that. So visible light's right in the middle of the electromagnetic spectrum. It's not harmful. It's kind of a medium length wave, medium frequency. And then you can see on like this chart over here that radio waves are going to be over on the left hand side. Those are super long waves. Okay, so they're low frequency. They're very large. They're long, long, long waves. So one radio wave could literally be like a city block in length for one wave to occur. And then you move into microwaves, are a little more frequent. Infrared waves are higher. Visible, right in the middle, like I said. Then you get into ultraviolet, which hopefully we already know, like skin cancer and stuff, is harmful to you. X-rays can be harmful, and gamma rays we talked about last class. So gamma rays are the highest amount of energy out of all of these, and the most harmful as well. So all of these forms of electromagnetic radiation make up this spectrum that we're going to talk about. Okay, so it's basically any energy that moves in a wave. Okay, so it's usually light, heat, sound, sort of, sounds kind of different. Anyway, so properties of light, all light can move at a constant speed, like visible light, I should specify. So visible light moves at a speed of 3.0 times 10 to the 8th meters per second. Okay, it's very, very, very fast. It's much faster than sound. And that's kind of why, like, this is more of a physics concept, but like, that's why if you are ever like across a lake, maybe, and you're in a cove, and like the neighbor across the way is like working on their dock, you can see them like hitting something or like hammering. And then you hear the sound later. Same thing with like lightning. Like you see the lightning and then you hear the sound. Because light is traveling way faster. The light's getting to your eyes a lot faster than the sound travels across. So the type of electromagnetic radiation is going to be dependent upon the wavelength or the frequency. So like I kind of talked about a second ago, if you have a short wavelength, that is high frequency because the waves are occurring very quickly in a short amount of time. And then if you have a long wavelength, that's low frequency. So lots of different things that we can use different types of frequencies for. So it's kind of cool. We've kind of learned how to manipulate that, and kind of like the technology has developed to receive these different frequencies of energy and to be able to like translate that into something. Okay, so I talked about this a little bit. So wavelength is the length of one full cycle. Okay, so like one full like up and then down and then back up. Okay, so like whoa, that's one full cycle. The frequency is how many waves pass in a certain amount of time. So normally frequency is measured in hertz is the unit. So like just Hz here would be the hertz, and that's cycles per second. So how many cycles are occurring every second. Okay. These two things, wavelength and frequency, are inversely proportional. Okay, so as wavelength increases, frequency decreases, and vice versa. This mathematical relationship is helpful if you're trying to solve for like the wavelength and you have frequency, or if you're trying to find the frequency and you have wavelength. So the speed of light, which we know, speed of light is a constant. It's 3.0 times 10 to the 8th meters per second. That's always going to be the same. Speed of light is equal to wavelength times frequency. So this little upside down y is called a lambda. It's a Greek letter lambda, and then that's just a v for frequency. You may also see that as an f sometimes for frequency. It's technically a velocity. That's why it's a v, because it's waves per second. So it's a displacement per time, which is velocity. Anyway, so that's what we're looking at there. Okay, so now we're going to start talking about the photoelectric effect, and this gets into some of your scientists that you guys did some research on. So photoelectric effect is talking about like the phenomena that electrons can be released from metals under certain conditions. So if you have a certain amount of energy coming in, that those waves of light energy or heat energy are going to be hitting the surface of this metal, energizing these electrons, and they're going to exit. That requires just the right amount of energy to make that occur. We're going to talk about that in a second. Okay, so in 1900, Max Planck is the person that kind of figured out the photoelectric effect was something that happens. And his idea, like kind of what he's known for, is this term called a quanta. So a quanta of energy is the minimum amount of energy it takes to cause the photoelectric effect to occur. Okay, so it's how much energy can be gained or lost by an atom, depending on how it's moving inside of the atom. I should say gained or lost by an electron. depending on how it's moving inside of your atom. So this is Mr. Max Planck. There's actually a big research facility down in South Florida um, dedicated to him. It's in his name, so kind of cool. So there is also Planck's constant. Okay, we'll do a little bit with this formula and like a little bit with the speed of light formula from before, but not a whole lot. This is kind of getting more into physics territory. So we have E, which is energy. Move my face again. It's annoying. Okay, so here we have E is energy in joules. Okay, so joules is just a unit for energy. H is Planck's constant. So he figured out that if you multiply the frequency of light or radiation by this constant, by this number, every single time it's going to tell you how much energy is being released or absorbed. Okay, so this is his constant. You don't need to memorize it, but it's just be aware that it exists. So if you see a lowercase h, it is Planck's constant. It's 6.626 times 10 to the negative 34th joules seconds. So V again is the frequency of radiation. Move my face again. This is so weird. Okay. So you also have this relationship. Okay, this should be kind of familiar. It's kind of both formulas put together. So you have a little derived formula here going on. So with this relationship, you can basically solve for any missing variable out of this. Okay, so if you're trying to find the frequency, which we know is V, but maybe we don't have the energy, we don't know how many joules of energy are being produced. If you have the Planck's constant, which we know we're going to have, and we already have the speed of light, you can sub this in and figure out wavelength. Or if you have wavelength, you can sub that in to figure out the frequency. So we're not going to do a whole lot with that, and that's not what we're focusing on today. So we'll get into that when I'm back. Okay, so then we get Albert Einstein. Okay, he's 1905. Oh my gosh, it's 10:30 already, guys. 1905, Albert Einstein. So he expanded on that theory and said that he believed that light behaves both as a particle and a wave, mostly because of how it interacts with other particles of light. So if you have light, like two beams of light shining together, they're gonna hit each other and like cause these patterns of like can't think of the right word. They interrupt one another though. So if you have two sets of light coming together and you're looking at it like they're waves, when they cross, it's interference. So you get these periods of like places of high energy and then places of no energy where they've canceled each other out or they've amplified one another. So again, that's more of a physics thing, but that's what Albert Einstein came up with. So he figured out that light behaves as both a particle and a wave because the way it is transmitted is like a wave, but the fact that they can cause interference proved to him that it behaves as a particle. There must be something there. Okay, so Odie's over there, he's groaning. So here, this is Einstein's relationship here, and this is similar to the other ones that we were just talking about. Okay, so the energy specifically of one photon is equal to Planck's constant times the frequency. Okay, so basically what that's telling you is Einstein saying that there has to be a certain frequency in that light wave to cause a photon of light to have a certain amount of energy. So you have to have enough energy coming in to cause a photon of light to be released. Okay. Let me see. Oh, that's what I was looking for. Okay, I'll go back one. All right, so then that brings us to the line emission spectrum. Okay, so the whole point of Albert Einstein saying that there's a certain amount of energy in a photon of light, and it has to do with the frequency, is that when these electrons get energized, they like jump out to the next energy level, right? Because they have so much energy, they cannot exist that close to the nucleus, so they're going to jump out here. As they get more energy, they're going to jump out here. They'll just keep on moving out until they run out of rings to jump on. But you get light being produced when that energy from in those electrons is released and they go back down to their ground state. So you have this vocab. So you have ground state is going to be the kind of the natural position of the electron. So a regular electron in like a Bohr model type shape, it's going to exist kind of in its own little area, right? So if it exists on the innermost ring, then that's its ground state. The excited state is when you have added energy. So we've added maybe light energy or heat energy, or radiation energy, gamma rays, and things like that. And these electrons get all this energy and they cannot exist here anymore, so they have to jump out. Okay, so now they're out here in these outer shells. When they drop from the excited state back down to their ground state, they have to get rid of that energy, sorry. So when they drop back down, they're getting rid of their energy and it's being sent off as a photon of light. Okay, so that's kind of what this is supposed to be showing here. So you've got these electrons that would naturally exist kind of, on these innermost shells, and then you give them a bunch of energy. They have absorbed all this energy, so now they're going to like jump out here. Okay, so they're going to move out, move out, move out. Whenever they finally do release that energy and they go back to their ground state, as they move back down to their ground state, they are releasing photons of light. So that's your ground state, excited state. The line emission spectrum is a little bit different than the electromagnetic spectrum, so don't get those two confused. Line emission spectrum is specifically talking about the visible light that is given off by any kind of substance. So the line emission spectrum is kind of like the fingerprint for every type of molecule in every atom that exists. Each atom on the periodic table, each element on the periodic table has its own specific line emission spectrum, which is pretty useful. So if you're looking at something that is maybe an unknown substance and you're trying to identify it, you can energize it and it's going to produce this spectrum of light. And if you can capture that spectrum of light and compare it to the knowns, then you can identify the missing. So this is what we're going to get into pretty soon with a flame test lab. So you guys will be burning different salts in class and observing the color of flame that's given off, that's produced. So, and you'll be able to identify some unknowns with that. So it's kind of a fun lab. As long as we don't have any more bonfires, but we'll talk about that when we get there. Anyway, so this is kind of like the fingerprint of each element. That's what you want to know. That's also why like neon lights are a thing. So if you take gas, any like gas out of the noble gases, and you put it inside of a glass tube and you energize it, it's going to produce light, right? So you are producing this specific set of lights that when you look at it from a distance, it might appear blue or green or pink or something, and that's what neon lights are. All it is energized gas. Okay, so we talked about this already, but quantum theory is what we call it when that excited atom, not an atom, that should say electron. It's when the excited electron falls from its energized state back down to its ground state. Okay, and in that process, it releases a photon of light. That's quantum theory. Okay, quantum theory. It's when excited electrons go back to ground state, they give off light, right? This is your electromagnetic spectrum. There's a video under the resources and extensions tab. So this, I think you guys are fairly familiar with, but there's actually a pretty good resource on this if you wanted to like screenshot it and keep it in a folder. That would probably be a good idea. But you do have like all of these variables listed down here. Gives you some of these relationships and stuff, so that would be useful. Different things that different types of waves can be used for, who discovered them, that kind of thing. Okay, so now we're going to get into Bohr model and Lewis dot diagram. So this will be a lot faster than the first part of the slide, sorry. So we're gonna start talking about Bohr's model. And Bohr's model is like the classic model of an atom. We have the rings and it's nice and neat. We now know that that's not really how electrons exist around the nucleus. They don't follow like a perfect pattern, but I think one of my kids is awake. Okay, no one's awake. It's just my dog snoring. Anyway, so so we'll get into that a little bit soon enough. But as far as we're concerned for drawing Bohr's model, it is still useful to show how many electrons are existing in each like orbital and suborbital. We'll get into suborbitals a little bit more when we start talking about VSEPR theory, which is next class or the class after. Seriously snoring like a little old man. Oh, it is. Okay. All right. So this relationship that we talked about earlier, we have energy is equal to Planck's constant times the frequency. Einstein talked about that. Planck talked about that. So de Broglie kind of alluded to it. So whenever you get in here and start looking at this, you're going to figure out on your periodic table that there's a nice little pattern to help you identify how many electrons exist on each energy level and like which energy level you're on. These are referred to as quantum numbers. So there's a couple different things that we'll associate with that. But again, you can kind of see in this example here where we're associating the amount of energy released to how much frequency was originally added to that atom. And then you have n equals 1, equals 2, n equals 3. Those are going to be your energy levels as you move out. So the higher the energy level, the higher that quantum number, the further away you are from the nucleus. Okay, so here is de Broglie. I'm going to move my face. Oh my goodness, I'm just messing this up today. Okay, Okay, so electrons is waves. So de Broglie was the first one to come up with this. And I know it looks like it says broccoli, but it does not. It says de Broglie. So in 1924, for like 20 years after Einstein made his theory about light behaving as a particle and a wave, Louis de Broglie came in and hypothesized that electrons can also behave as a wave particle. Electrons are confined. We know that electrons are kind of confined to their energy levels, but within their energy level, they behave as a wave. So we're saying that electrons don't just spin around in this nice little circle, that really they're kind of moving at their own frequency, and whatever frequency they have depends on which energy level they exist on. Okay, so this is the de Broglie wavelength like theorem. Again, you get a lot of those same mathematical principles. I'm not going to make you guys use this one, but I'm just going to put the comparison on there. So if you look at this, you have N1, which talked about a second ago. That's going to be your innermost ring. It's the lowest energy ring. And you have a pretty large wavelength, low frequency. It matches with the electromagnetic spectrum, okay? So the lowest frequency had the largest wavelength. It's the least amount of energy, which is like radio waves. And then as you get on like past to the second energy level, the third energy level, out to the fifth, sixth, however far you are going, you get higher and higher frequency. Okay, so this ties it all back together in saying that these electrons have to have a certain amount of energy in order to exist further away from the nucleus. Okay, so if you have electrons far away from the nucleus, they have to have a lot of energy to be out there because the nucleus is attracted to these electrons. Okay, the nucleus doesn't want to get rid of its electrons. So the nucleus is pulling these electrons back in. So in order for these electrons to be able to get further out on these other orbitals, they have to have quite a bit of energy to do that. So de Broglie is just showing it as a wave particle, saying that electrons behave both as particles and move in waves. Okay, so we have Heisenberg's uncertainty principle. So this is Werner Heisenberg, and this is a few years after de Broglie. And basically what he came up with, his principle states that you cannot know how fast an electron is moving and exactly where it is at the same time. It's impossible. Because in order to know where an electron is, you would have to essentially take a picture of it, right? You would have to hit it with some sort of energy, so whether it's light energy or X-ray energy or something, something has to touch that electron and then be bounced back in order to measure the distance, okay, to figure out its position. In the act of doing that, since electrons are so tiny, you're just going to knock it right out of its orbit. So by the time that information gets back to you about where that electron was, it's no longer there. Okay, so that's the uncertainty principle, that you can figure out how fast it's going, you can observe it and figure out how fast it's going, but by the time you figure out its velocity, it's no longer where it was. And if you figure out its position, the act of figuring out the position has changed its position. Okay, so you cannot know both. Schrodinger is kind of a weird dude. This is a pretty cool video. If you are interested in like quantum mechanics and like theory of relativity and stuff in physics, this is a really neat video. I usually show like part of it during class, and I'm going to skip it right now just for time's sake, but I would encourage you to go back and watch this video when this is done. So Erwin Schrodinger also agreed and added on to the hypothesis that electrons exist as both waves and particles. Okay, so they're moving around in waves and they are tiny little particles. And he kind of just piggybacked off of Heisenberg. So he was saying that there's a certain probability that an electron exists in a certain area. Which makes sense if you think about it. But he was the first person to like propose this. So his theory is that an electron, because we can't identify exactly where it is or exactly how fast it's going at the same time, that we can only give a probability of where it should be located. So we have to say then that an electron both equally exists in this exact place and does not exist in this exact place at the same time. So that's kind of what he was talking about with his cat in the box theory. So he basically, is the cat dead or alive? You won't know until you look, and by then it's too late. So anyway, if you want to know what that's all about, watch the video. Okay, so atomic orbitals. We do know that electrons do exist in orbitals, okay? So this picture down here, I'll move my head again. This picture down here just shows you kind of like what these layers of orbitals look like. It's not a perfect picture like a Bohr model, okay? So atoms don't actually exist in like nice little rings that are stacked little concentric circles. They exist in these three-dimensional orbitals. So that's where your quantum numbers come in. We did allude to this earlier. So as you increase your energy, basically those levels get higher. So if you have a higher amount of energy, the electrons have more energy, they're going to be further away from the nucleus. And the amount of energy they have tells you where they exist. Okay, so this picture, move my head once more. This is showing you the nucleus. Okay, so, and we have a three-dimensional plane here. We have X, Y, and Z. So we have the nucleus down here. This is showing you the first orbital. And don't worry so much right now about like what 1s means or like 2p. We have a whole day for that. But this is showing you that on that innermost orbital, this is kind of your shape. It's a sphere, small sphere around your nucleus. It only holds 2 electrons. That is important today. Only holds 2. So the innermost sphere is small. It can only hold a low amount of energy. therefore it can only hold 2 electrons. The next level out pops it out. So now we're in 2s orbital, which again, we'll get into that another day. But you start to fill in. So you get to add more electrons. Then you start to add more electrons and more electrons. Okay, so every time you add on another layer, you're adding more and more electrons. And each layer that's further out and larger can hold more energy. Okay, so this would be like your second ring, basically. Each of these little figure eights can hold 2 electrons, and then this larger sphere can also hold 2. So the very innermost, the tiny one, holds 2 electrons. The second level can hold 8, which hopefully you're familiar with. Okay, and then you would get bigger and bigger. So now you have this huge sphere that kind of encompasses all of that. It can hold even more electrons. And you just keep going and going and going until you have enough room for everybody. Okay, so Bohr models. This is what we are actually working on today as far as like drawing them out. So a Bohr model is going to tell you the approximate location of electrons according to their energy. Okay, that directly relates to your periodic table. So if you don't have your periodic table out yet, get it out, and you guys can write on your periodic tables and fill in like your valence electrons and groups and stuff that I'm getting ready to talk about. So each shell on a Bohr model can hold a certain amount of electrons, which is what I was just talking about. So if you have your nucleus, okay, it's this little green ball here, the innermost ring can hold 2 electrons maximum. Okay, so if you look at your periodic table and you determine that this atom has 8 electrons, you start out putting them on the innermost ring. You have to fill it up from the inside out. So you put 2 electrons on the innermost ring, and then you start building the next ring. Okay, it can only fit 2 on the inside. So innermost ring holds 2. The next ring can hold up to 8. Okay, so if you have 8 more, they would be placed on that ring. The following ring can hold up to 18 and then up to 32. Technically, I believe the 5th ring could hold 50. Don't quote me on that, but nobody draws Bohr models larger than this because that will get you pretty far down on the periodic table. So anyway, some examples here and kind of how to do it. This tells you too kind of how to do it. Oxygen, if you look on your periodic table, oxygen's atomic number is 8. Okay, so that means that it has 8 electrons if it's neutral. So we're assuming that it's neutral if we're just looking at the periodic table. You have 8 electrons you have to place on here. So you draw a nucleus, and then you draw your first ring. The first 2 electrons go on the innermost ring. Okay, so if you have already placed 2 electrons, you have 6 more that you still need to place. So those 6 would fit on the next ring, okay, because this second ring can hold 8 all on its own. So technically you could have placed 10 electrons here, but we only needed to place 8, so that's where we're at. Please spread them out, okay? So we're representing the location of electrons. In no situation would you ever have all of your electrons together in one place. They're always going to be equally separated because they are like opposing one another. So silicon's another example. This, again, not a great example of like having them spread apart, but if you had 14 electrons, you would put 2 here plus these 8, which would get you up to 10. You have 4 left, so you would have to add another ring because this ring only holds 8, and then you just keep on going further and further out. Okay, so this is just a bigger one. Oh no, this is just a bigger one here, kind of explaining that. Okay, so more examples. So 2, 8, 18, 32. Remember that. Okay, so you try. If you want to pause this for a moment and try to draw the Bohr model for carbon and then compare it, go ahead. Okay. So I'm going to go ahead and just kind of like go through it here. So if you have carbon, it would look something, like this. Okay. So carbon, where's my head again? I just cannot figure that out. The right place to put myself. So you have 1, 2, 3, 4, 5, 6 electrons because we're assuming it's neutral. So 2 fit on the inside. You have 4 remaining, so you put those 4 around the outside. Same thing for potassium. Okay. So you have quite a few electrons here. You just start with the inside, go to the next ring, go to the next ring, go to the next ring. Okay. Lewis dot diagrams. Let me see. Oh, I need to go back actually. Hold the horses. I don't go back. Okay, right here. All right, so with potassium, I wanted to point out that you have 2 here, right? And then you have 8, and then you have 8 here, and then it jumps to 1. Like, so we did talk about how like this should be 2, 8, 18, 32. The only exception to that is before you hit the transition metals. So if you are in like the top right corner of your periodic table, it does have the pattern of 2, 8, 8, 18, 32, and so on. It just has to do with where it's located on the periodic table, which will make more sense here in a second when I show you that part. Anyway, so Lewis dot diagrams. These are representing the same thing a Bohr model tells you, but it's only showing you the outermost electrons, which is super important, especially for next unit, because we're going to start talking about bonding, the different types of bonding, and how to figure out how that's going to work, and like what type of bond it's going to make, what kind of energy it gives off, and yada yada. So valence electrons only. So again, just the outermost electrons, these are the only ones involved in bonding because they are trying to become stable. So it's kind of like same idea as like an isotope. Like the isotope, the nucleus was trying to become stable, so it was like releasing particles and energy to make that happen. Atoms by themselves want to become stable by filling up their outer shell. So they want to have 8 valence electrons. They want to have a full outer shell. So in order to do that, they're going to start bonding. So you have to figure out on these how many valence electrons you have, and that has to do with which, like where they're at on the periodic table, which I'm going to have you guys right here in a second. So carbon has 4. You always want to start at the top and put 1 dot on each side until you have filled that up, and then if there were more, you would start doubling them. Okay. You always want to spread them out because you're representing like the possible ways that these could bond with other atoms. Okay, so this is going to be a huge hint. Write this on your periodic table. Okay. These are the group numbers along the top. I feel like these might already be on your periodic table, but this is telling you how many valence electrons there are. Miracle. Makes your life so much easier. So group number 1, every single element in this column has 1 valence electron. So it would have 1 dot. Same thing for the second one. They have 2 valence electrons. Transition metals in the middle, we're not going to talk about those right now. They have a special case. So those will come later. But you get over here, it says 13. No, you're not going to have 13 valence electrons, okay? You just forget about the 1, okay? So everything in group 13 has 3 valence electrons. Everything in group 14 has 4 valence electrons. 5, 6, 7, and 8. When you get to 8 valence electrons, it's stable. It's probably not going to be bonding with anything unless it's like a super special situation. So remember those. That's how you draw your Lewis dot structures. That's how you know how many dots there are. Okay. Label your periodic tables, please. Make sure that you understand that the groups are vertical columns and the periods are horizontal rows. Okay, so the groups are telling you how many valence electrons there are, and the rows are telling you what ring you should be on whenever you're drawing your Bohr models. So if you have a Bohr model that's like located here in this yellow spot, you automatically know it's going to have 3 rings because it's the third one down. So green would have 4 rings, blue would have 5 rings, and so on. So you guys could pause me for a second if you want to try this on your own. I'm just going to talk about it though. So calcium, you would try this, you'd figure out how many valence shell electrons it has, and you would start drawing them in. It only has 2. Okay, so it's in group 2. calcium has in group 2, you're going to place them here because ideally it's probably going to be bonding with another one on either direction here. Okay, bromine, go in, figure out what group it's in. It's in group 17. It's going to have 7 valence electrons. Okay, so you hopefully saw the pattern that they were placed on there, right? So you go 1 at the top, right, bottom, left. Now you double them, double it, double it. If it had an 8th, you would fill it in, like right here. Woo! Done with the notes. So I'm going to talk about the assignments real quick, and then I will shut my face. Okay, so this is one of the assignments you guys are going to do today. This is the electromagnetic spectrum worksheet. Basically, you are just labeling these. So you have like 1, 2, 3, 4, 5, 6, 7 up along the top. You have these letters down here. If you want to be kind of lazy about it, you can just put the letters up there. If you want this to be useful for you later, I would write it out so you know, like, these are gamma rays, this is visible light, because this is going to be something that you could use as a resource on a quiz or an exam later. You also have a couple questions here, just kind of like analyzing the patterns and trends that you see. Okay, very last one. Okay, so Bohr models and Lewis dot diagrams, that's what this worksheet is about, and it is 6, 7, 8. It's 8 of these that you're going to be drawing, and then the follow-up. So you guys can work with somebody on this if you want to, just for like dialogue, so you guys can discuss it and figure it out. Everyone needs to turn in their own stuff, so please. So on here, you guys are kind of looking to see what you have and then figuring out the rest. So on the first one I gave you, the element was carbon 13. Okay, so the atomic notation, see if I can get this pen thing to work very well. Okay, so you know that carbon is a C. 13 tells you right there in the notation over here that it has a mass of 13. You can look up on your periodic table and see that carbon has an atomic number of 6. And this one we're assuming is neutral because it doesn't tell us that there's a charge or anything. So we're not going to have anything in this top corner. So now you can come in and figure out how many protons, neutrons, and electrons there are. So for this one, since it has 6 protons, it's 6. Electrons, if it's neutral, it'll be 6. And then neutrons is going to be mass minus the protons. So this one would be 7. Now you can come in, and this is kind of new. So the number of energy levels versus the valence electrons. This is where your groups and periods come in on your periodic table. So you can look on your periodic table, figure out what group it's in. It's in group 14. So it's in group 14, so it's going to have 4 valence electrons because carbon can bond with like anything. It's kind of cool. Energy levels has to do with what period it's in. So it is, I don't have a periodic table handy. It's in the second. It's in the second, duh, because it only has 6 electrons. Never mind. So energy levels, it is in the second energy level. Now you would come in and draw a Bohr model. So I'd say like, okay, this is my nucleus. I am going to draw one circle with 2 electrons on it. This is not pretty, guys. I'm going to draw another one with the other 4 electrons hanging out. And then drawing your Lewis dot diagram. So Lewis dot diagrams are just going to represent your valence electrons. They're going to have all of these guys. You're going to separate them. Boom, you're done. Okay, so that is kind of just what you're doing for these. Keep in mind, like, there's a couple others that are like, they look a little different than this, right? So this one gives you protons, neutrons, and electrons, so you're going to have to write out the notation yourself. This one, I'm going to give it a charge. I need to edit that. Anyway, so that'll have like a charge on it, which means the electrons are not the same as the protons. So you would have to figure out, like, is it +1 or -1 or whatever it happens to be. And then you guys have a couple of questions down here. So please do treat this as like a partner assignment, not a group of like 3 or 4 or 5, please. But please discuss it with your partners. So if you have questions, let me know. It is 11 o'clock and it is way past my bedtime. So I think that was it. All right, I'll stop talking now. Hopefully that was helpful. Hopefully you skipped through any parts that you did need to see. Watch the videos under the resources tab, especially the Chernobyl and Radium Girls. Those two are good ones. Watch Schrodinger's cat video from the slides if you are interested in that, because you do kind of need to know what you did. And then get these 2 assignments done. I will be here this afternoon, so come stop by if you need me. Send me an email. Come in during ACT Lab tomorrow, whatever. Tomorrow's Wednesday, but you know what I mean. Come find me. Please don't wait until Thursday to be like, Miss Blaine, I have no idea what you're talking about. So have a good day. I'll see you guys later.